So this article is related to urban topography with building footprints with Python flood simulation. So in this article, we have developed a 2D urban flood simulation implemented in Python using the diffusive wave approximation of shallow water equation to predict flood dynamics in complex urban environments as well. So the 100 years design storm with a triangular hydrograph drives the simulation, generating the detailed output of water depth, flow velocity, as well as the flood hazard indices throughout the 150 by 150 grid domain as well. So the thing is that in this six outputs, we have generated a maximum inundation depth, peak velocity, and as well as with the streamlines, hazard index maps, and outlet hydrograph flood, which areas will affect through flood and how it will affect due to different different speed, velocity, its depth, its urban planners, its crops. It also affected the populations of living areas as well. So that's why we need to identify its flood simulation through its velocity, its depth as well. Okay, so this is a simulation and how we can identify the flood hydrograph for the maximum depth, its flood volume as well. So these are the storm event characteristic. Basically, these complete article will predict the flood duration, its peak, its normal value, its depth, and its affected areas, and the planning of like we can plan through this article. We can plan safety measures from our specific areas. Okay, so that's why this is a growing urban flood crisis. Yes, basically climate due to climate change, intensified extreme precipitations events, while rapid urbanization has replaced the natural permeable, permeable surfaces with impervious concrete and hard as well. So the combination creates the perfect conditions for catastrophic flood events and overwhelming aging drainage infrastructure as well. So the limitation of traditional flood modeling approach basically provide us the one-dimensional model. A conventional flood prediction methods basically rely on only one-dimensional model, treat the urban drainage system as linear channel. These approaches fundamentally fail to capture the complex two-dimensional flow pattern that emerge when water interacts with buildings as well. So that's why traditional methods are not be used in a modern world to save the urban areas as well as specific flood conditions. Okay, so the need of advanced numerical solution simulation is that modern computational approach must capture how water moves around building obstacles and accumulates in streets, depressions, as well as drain through the manhole and networks as well. So the planners and engineers require the predict models that can simulate the flood propagation in real time to support the emergency response decisions as well. So the two-dimensional shallow water equations as the foundation is that we need to check the flow depth and velocity in terms of temporal variations as well. So the formulation accounts for the gravitational force driving flow down topographic gradients while the incorporating frictional resistance from the surface roughness. So the diffusive wave approximation also provide us the local and convective acceleration terms that are negligible compared to the gravitational and frictional force. So the approach dramatically reduce the computational complexity while maintaining the accuracy for flows, as well as the initial effects are minimal as conditions satisfied in most urban overflow overland flow scenarios. So the capturing urban complexity through the feature representation also provide us the road networks serve as efficient convenience channels with low roughness coefficients that accelerate water transport as well. So the drainage system, including the manholes and underground pipes, as well as provide the critical capacity for removing the water from the surface as well. So the special arrangement of these features determines the flood propagation patterns, ponding locations and overall system vulnerability as well. So the Python has enabling technology to identify the uh, complete researchers and protections practitioners and students help out how we can simulate the flood complete mechanisms and model architectures and numerical implementation. Yes, we have used different techniques in terms of hydrographs representing that design storm events, and also we can implement the rainfall which is applied to time varying source as well, and the boundary conditions of domain edges allow the water to exit the system. So the comprehensive output visualization also provide us the effective flood modeling, as well as the velocity fields with streamlines reveal the complete flow paths and intensities and hazard index maps as well. So the hydrographs at downstream outlets characterize the system response on timing, and time series analysis tracks the evaluation of flood characteristics. So the application and contribution of urban resilience. Yes, we need to for infrastructure planning. The model enables evaluation of drainage system capacity and identification of vulnerability hotspot, requiring the intervention as well. So the problem statement, yes, problem statement is that we need to escalate the urban flood disasters driven like climate change, as well as we need to discuss how the conventional method are not suitable for the modern world conditions, flood conditions. That's why we need to discuss, and we need to design this complete model. So the mathematical approach is here, and in which we have identified the complete equations and methodology, as well as the model parameters, and then design Python simulation with urban topography with building footprints as well. These are the building footprints as well as an urban topology with building footprints, because basically these are the path for the grid cells as well as elevations as well. And then next one is we have identified the maximum inundation depth during the storm events, like how the water will flow in these times as well. Then also we have added the peak flood flow velocity field as well. These are the velocity levels, and in terms of different uh, peak flood flow velocity. And then we have identified flood hazard index output graph. Then we have just added the how flood hydrograph at downstream outlet, and then identifies the temporal evaluation of flood characteristics as well, and then results and discussion with the conclusions are added with as well as the references. Let me just provide you the MATLAB, sorry, a Python based demonstration. Yes, this one. Okay, first of all, you just need to remove the previous one. Okay, so this is the complete urban flood simulation model. These are the Python libraries. Then we have identified the parameters here, defined here, reference infrastructure parameter, then time parameters, as well as we have added the add street depressions. Then we have generated the complete road networks, then drainage system, apply rainfall, then compute fluxes as well as the compute gradients in x direction, y direction, then Manning's equation for flux as well as we have applied the building barriers, water depth, then apply drainage system. These are the all the equations for the main simulation and visualizations of different scenarios like urban topography and building layout. Then we have added the peak flood velocity field and then flood hazard index as well as the time series maximum depth and volume, flood volume as well. Then summary. So these are the output results of urban topology with building footprints, output results, and maximum inundation depth during the storm event as well. Then peak flow, flood flow velocity field as well. Then we have also generated the flood hazard index as well as the rainfall, downstream outlet, then temporal evaluation of flood as well. So if you need to ask anything, you just ask me, I will answer your questions.